if you'll be lucky, then some of your classes will be in the new buildings. Yeah, I just been informed. I'm going to be assigned to take ES301, and then yesterday I was informed the class will be in that building. And I feel, oh, okay. And then this morning I was informed, oh, they swap and my classroom will be still here. That makes me happier. Because this I don't need to walk that long. But I think for you guys, maybe you would prefer to go to the new environment. So now for these sections, I just want to talk about from a little bit more beyond the Hoffman transfer. So this one basically is the general, I would say, coplanar's transfer. So basically this one is the extensions of Hoffman orbit transfer. Okay. So again, let us to recall what is a Hoffman transfer. The Hoffman transfer basically is here. We consider the original circular orbit, and then we consider our target circular orbit. And their transfer basically is to take the half cycles of the elliptic orbits that is to tangent to both of the original and target. So that is the definition of the Hoffman transfer. And now if we consider extension is this, and okay, so again here our target is still, we consider is two circular orbits. So this is the initial, and this is the target. Okay, so again, we still consider it is circular, and later on we were going to extend to other elliptic orbits. So now the transfer is done by, rather than using the tangent, cotangent elliptic orbit, and here we want to extend is more thinking is the, are we able to say the first case is, we call it by elliptic transfer. And by elliptic transfer, that means we're using two elliptic transfer orbits, and how to do that one. So right now, again, this is our starting point. Okay, the same thing as we done here. And now, rather than putting the rendezvous at that point, we design our point is here. Okay, so connecting from here to here, that is using the half of the corresponding elliptic. Okay, and then from here, using this point and this point, basically the 3 points are at this aligned. So here, from here, we corresponding to another half of the transfer elliptic orbit. The joint should be tangent here. Okay, so the both are elliptic. this is the same thing. And for the second one, is we call the parabolic. So that one let me show this again. This is our initial, that is our target. And this is a target. And the both are still circular. Okay, so this is initial target. So the parabolic, that means we're starting from this point here, and we simply taking a transfer orbit. This transfer orbit is so unique, and basically we take up a parabolic. And you know the parabolic is to bring the things to infinity. Basically, there's a no closed form, right? So basically, this one is going to a certain way or proportion to infinity, deep space. And then from there, then we bring it back. This is a theoretical. In practical, we won't be able to do this one. The two are both parabolic, but they have the different features. This one has the larger RP than the inner one. Okay, so basically this is the focus, occupied focus here. So for this consideration, we could do some, there's another kind of extensions. And so I believe because we already have the information about geometry, so from here, if we really want to, for the learning, for exercise, we are able to calculate the delta V at here and delta V at here as well. Okay, so simply this is a little bit more exercise. And here I can do, we can exercise how about for this one, parabolic first. Okay, so let me get a point. So let me call this is point 1. And let me call this a point 2. Okay, so now I'm going to demonstrate how to calculate the delta V is necessary for making this happen. So for parabolic, and delta V1 equal to V this means the velocity on the parabolic and minus V on the I want to make a good notations. How about I give a name? This is the circular this is circular, I don't know, how about already I have this one, how about I just use I? Okay, so initial orbit, VI, and at point 1. Okay, so hopefully here this is the I is the initial orbit at point 1. Okay, so that's what I mean. So this is the parabolic transfer orbit. Okay. So from here we can determine is this. So V parabolic is how to determine this one. So again, here we know the specific mechanical energy and equal to V squared over 2 minus mu over R. And for parabolic orbits, we know the specific energy by definition equal to 0. So from here for parabolic, then we can have V equal to squared 2 mu over R. Okay. And if you remember, we have definition called as escape speed, and that is the speed defined when R equal to the radius of the Earth. Okay, so that's the definition here. So here we can plug in that formula here. So equal to 2 mu over R. And at point 1, so at point 1, so at point 1. Okay. So at point 1, that means R equal to, again, so let me say this is R1, distance R1. And V at initial target at point 1, and that is a circular orbit. And circular orbits we have is this. Again, specific mechanical energy equal to V squared over 2 minus mu over R. And for circular orbits, for elliptic orbits, we have is energy equal to minus mu divided by 2a. Right? And 2a is the major axis. So from here we have is V, and have the more general information is there 2 mu over R and minus mu over A. I think that's it. Okay, so plug in there. So we have 2 mu over R minus mu over A. So for the initial, which is a circular orbit, the at point 1 R equal to R1, and A is the radius, so it's R1. So from here, this one equal to mu over R1. Okay, so therefore, from here we can determine, so therefore this one we plug in here everything, so let me write it out. So basically that is equal to square Q minus 1 times mu over R1. Okay, and also you can see I want to express in terms of V1, so pretty much we can express this number equal to I1 here. Okay. So the same thing, we can repeat the similar process at point 2. So this is at point 1. So from here you can see when I do this one, I will go away onto my scratch and paper to whatever necessary, and then jump back here. Okay. Otherwise, too many formulas, I won't be able to, from the very beginning, very organized to see what kind of equation I would need. Even at this moment, I spent a couple of minutes to prepare my cheat sheet. I still cannot do it unless I need to memorize my lecture notes, but I won't be able to. Okay. So I point to the same thing here, the delta V. And here we simply taking up is, say, delta V is, if we consider, say, is again pay parabolic transfer orbit at point 2 minus V on the target orbit at point 2. Okay, so that is the target. At point 2. So that is the parabolic transfer. Okay. So they will take up the same patterns of the formulas. So let me skip off the detailed calculation and directly come up to here. So again, that is the square 2 minus 1 times V and T2. So therefore, the total delta V for by parabolic will be equal to delta V1 plus delta V2 here. So that is equal to square 2 minus 1 VI1 plus square 2 minus 1 VT2. Okay, and let me rearrange the results further. And so how about this? And for this way, I try to put the result as the non-dimensional factor. So how about this? I divide the both end sides by delta V and by VI1. Okay, so I divide the both sides by VI1, and again I want to go to the non-dimensional factors here. So this one is equal to square 2 minus 1 plus square 2 minus 1 VT2 and divided by VTI1. Okay. So VI1 equal to what we have done here is the mu over R1, and VT2 we have a similar pattern is mu divided by R2. Okay. So therefore, in this way, the equal sign will be equal to this one. R2 over R1. Okay. So further, that is this one. So from these scaling factors, we have the information is this, we can draw a line. So from here, say this is the scaling factors here, so that is R2 over R1. So relative ratio between the target and the energy and target. So that is the energy. The total velocity change, that means the fuel, the energy. So we can draw this curve, and that one is something like this. Here I schematically draw it. Okay, if we have a MATLAB, then we can do this one here. So basically, this is equation 1. Okay. Any questions? And here we simply do the symbolic and calculation. Once you have a number, you should be able to do it quickly. Okay. So from here you can tell is when it's more efficient when the ratio is large. So which means, and so kind of give us some ideas. Okay. Compared to original that is being exercised for more than 1 hour, and since the Wednesday last week, this week. So if I would ask you, say I give you certain numbers, say if this is R1, the same thing, we have the target radius is R2, the same thing, the same setup as we have here. So this is R1 and this is R2 here. Okay. Are you able to repeat the same calculation, determine the data V1 and determine the data V2 in terms of the symbols? Then you calculate data V. And in terms of that one is the functions of R2 over R1. I think you should be able to do it. Give it a try. Okay, and let me list out the result here for you. So in this way, the total, let me write using the different column. So the delta V, so this total, I would say Hoffman. Divided by, again, we scaled with the VI1. Okay, and that one, if you do that correctly, that should be equal to is 1 minus and okay, give a try. This won't take, it's a little bit tedious, but won't take too much time. And we have done quite a few examples and in terms of numbers. So right now you simply do the symbolic. So basically here, per our definition, basically this is R. And in terms of the parameter R, we can put the curve here. And if you remember earlier at the beginning of these chapters, I mentioned that Hoffman transfer is, in general, most of the time is the most fuel efficient. I would say most. And here is the evidence I'm going to show you. If you would draw that one, the Hoffman transfer is something like this. Let me call this equation 2. So if we place the two things together, that is the curve. And that is the total velocity change, which means the fuel. And the statement that the Hoffman transfer is the most fuel efficient is true only in this range. When the number, if we find the intersection, that number is 11.94. Okay, we can be more accurate, but that is one. So that means if you have your initial and target orbit relative size and that fitting into under the 11.94, then if you want to be the fuel efficient, you go to Hoffman transfer. Okay, and if your initial and target orbit size is larger than this one, then you have to consider other options. Okay, so that is the story here. And okay, so that is for this section.